So yeah, today I will talk about XRT. It's not directly related to XAS, and sort of stands out many of the talks that we've heard here before. But yeah, I just want to present a tool that can be very useful for all people on beamlines and in the labs who work on designing and commissioning and troubleshooting X-ray instrumentation. Though XRT is a rich, full-featured package, today I will focus on visualization aspect and visualization capabilities. So first couple of words about XRT in general. It's just two people behind it. It's Konstantin Klementiev from Max4 and myself. We describe XRT mainly as a library. So it's initially intended to be used in the code in the Python script by creating a small program or a small script that would solve some problems. Later, it grew up into something bigger with GUI and other nice things. The main idea, the main technique that we use is Monte Carlo. We sample lots of rays. We sample millions of rays, and then we use them to represent the beams, and we use this millions of ray for numeric integration in case of wave propagation later. And that's the main benefit, the main advantage of XRT. We can easily consume millions and millions of rays. That gives us precision and high quality of the plots. So initially, it was just a front end, just a plotting front, no, not just plotting front end, but also a wraparound shadow and some other ray tracing backends that had troubles back when we started 10 years ago. It's basically when Konstantin started developing it. I joined this project a little later. So it was it allowed to accumulate lots of rays even with shadow backends, and it could add a color to the plots. Having color as additional dimension is really useful. You can use color to demonstrate energy or phase, like in this case of the elliptical undulator. Or you can assign different colors to different diffraction orders going out of the grating. So it's nice to have it. Among other important features of XRT, so first of all, it's homogeneous. We don't use any third-party pre-calculation software. We don't generate any intensity maps or anything like that, like, for instance, Shadow is doing. Whole code is Python. We use some acceleration, but it's optional and it's in C. So in principle, it's easily readable. So whoever wants to contribute or to learn how the things are done in XRT, they are free to go to GitHub and read it. It's well documented as well. Again, unlike Shadow, we work in global coordinate systems. So if you define an optical element, it will be not just a distance from previous element, but it's real coordinate in real space, pretty much like you use it in real life. Since all modules belong to the same library, we don't use any intermediate file write-read operations. So all objects are stored in memory, and it gives us capability to calculate everything really fast. No writing to disk means high performance. We support GPU acceleration that is mainly used for some heavy calculations like direct integration of the synchrotron sources or wave propagation. In principle, this all works in regular NumPy, but with OpenCL and decent GPU, it's done within a matter of seconds or milliseconds instead of minutes, like in other codes of pure NumPy. So we recommend, if you use XAT, please try to set up OpenCL on your computer. It's not really complicated. Then we have some libraries to calculate material properties. And I will show it later in a demonstration. Yeah, I will show how to estimate the flux on the sample depending on the optical elements in the beam path. We also use real physical units, not just intensity in the number of rays. So we show photons per second, which is more meaningful than just abstract intensity. We can do ray tracing and wave propagation. I mentioned it in the beginning that we still use the same Monte Carlo approach to calculate the soul. And I'll show a couple slides with some details about how we do this. But in principle, we can easily switch from one mode to another and use rays on certain segments of the optical setup and wave calculations where it's necessary. Then it's not something special nowadays. But we have GUIs and yeah, lots of visualization tools, and some pictures from the 3D visualization is on the right side. So I'll just give an overview of different models of XAT. So we provide simple geometric sources and real synchrotron sources with real distribution, with real spectral properties. We can use some analytical formulas for simple models like bending magnets or wigglers, but we also use direct integration techniques for the undulators and custom magnetic structures like here. So we start from the very basic things. We calculate the trajectories and then calculate Fourier components. Yeah, in principle, we can calculate the beam for any magnetic structure. If you have your field table in a file, or you can, I don't know, use NumPy to generate a sign or anything you want, anything you want to test, anything you want to see how it will look in reality. Yeah, just a couple examples. I've recently was working on the 3-pole wiggler case study for the future CLS2. That one is intended for the infrared beamline, and that's 3 small magnets, and it was interesting to see what would the beam profile look like in the end. And actually it looks really complicated. There's an interference from different poles that gives rise to this complicated profile. Here as well, we compare our code versus SAW and Spectra, and in principle, there are some minor differences, code specific, model specific, but overall, all the features are in place. And in addition to this monochromatic case that any other package can do, we can make use of the fact that XAT can quickly generate the rays in three dimensions, angles and energy, and you can generate something into a finite bandwidth. And yeah, that's what you have in real life. You never have strictly monochromatic waves. Yeah, and then you can use this finite distribution to propagate it further, use it in ray tracing, and study, yeah, and see what comes to your sample in the end. And it will be more precise than just a monochromatic wave. Now, a few words about other capabilities. We support different shapes and surfaces. It can be plane, obviously plane elements, then most of the conical sections. What other unique features? We can do non-sequential propagation, and we can expose multiple elements at once and see how the beam is interacting with multiple elements. We can also use multiple reflections in a single element, like waveguides, or like in this example, it's a capillary, but it's a polycapillary, and it's a closed shape. It's cylindrical. That's really, well, I don't say hard. It's nearly impossible to simulate these things in other packages. At least I don't know how this can be done. Yeah, we calculate the intersection point with high precision down to picometers, and that allows us to take care about the phase, about the complex amplitudes of the beam, of the ray. We can also apply some surface distortions, though it's more of advanced feature, and you have to write some code to make use of it. We can calculate all material properties. We can calculate reflective optics, yeah, multi-layers, mirrors. Yeah, we can calculate refractive elements, filters, and CRLs. And material properties are applied or are calculated for each individual ray separately. So there are no intensity maps, there's no interpolation. So whatever is calculated for this specific point of intersection, for this specific ray with certain energy and direction, it's all really precise. We can also calculate energy-dispersive elements, crystals in Bragg and Lauer geometry. All dynamic diffraction effects are regarded carefully. And now a couple words about bending. So we use relatively simple, sorry, I'm wondering, yeah, that's here. We use relatively simple geometric approximation. So we just calculate how the crystal lattice normals are distorted during the bending. So we don't take into account all the tensions that's happening inside the crystal so far in the current version of the code. We've done some experiments in direct integration of the Takagi-Tappen equations, both for spherical waves and plane waves. Plane waves give you the reflectivity curves. If you work with spherical waves, they give you a real distribution of intensity of the diffracted beam. So this picture on the left is reflectivity curve in Lauer case. I believe it's 1 meter bending and 30 kV. I don't remember what was the thickness, but anyway, we can do this. But at the moment, it's really it's really slow because you have to define a really precise integration grid. And this would work fine on thin elements, maybe few microns thick. But in real life, it's rather millimeters, and the energies that people are interested in are tens of kilo electron volts. And if you increase the energy, you have to make the steps smaller, and that it ends up in grids that are have maybe 10 to 12 integration nodes. And though it's still doable, you can still calculate it, but it takes many minutes just for a single wavelength. And we're focusing on the highest possible performance. Something that people can easily do in the real ray tracing study. So if there's a task that takes many minutes to calculate on a powerful GPU, I think it's still early to open it to public, to me, at least. So we're thinking about different ways how to accelerate this. I know that there are some other packages that can calculate reflectivity profiles for band crystals, but all of them work with intensities, whereas we are calculated in preserving the complex amplitudes and really take care of the phase in order to propagate this beam further, and maybe if it further interacts with other elements that require the phase, it may be really important. So yeah, this is so far an experimental feature. We can try to run some test studies if anyone is interested, but it's still in the lab. Yeah, now if anyone has questions, yeah, before I start the live demo.
Okay, there's a couple of questions. Gabriel Mann had a question. Please, Gabriel.
Thanks, Jerry. Hi, Roman. Thanks for the talk so far. My name is Gabriel. I'm working as a senior postdoc at Uppsala University in Sweden. My question is about whether XRT can be readily adapted for simulating X-ray propagation through a stack of materials like an optoelectronic device.
Well, in short, yes. You have all the tools. I believe you're probably interested in applying some masks, if I understand correctly, right? Or
yeah, what I'm really interested in is to try to exploit X-ray standing wave using tender hard X-rays to do absorption and/or emission.
Yeah, so it's yeah, everything is possible. I don't see why it wouldn't be applied to a task like this. So the code is open. Yeah, lots of examples. If you have any specific questions, yeah, we encourage everyone to submit questions or how that's called feature requests through the GitHub. And yeah, we usually give some recommendations. If it's something is really impossible, yeah, we'll just study it and explain why and what could be improved.
Okay, thank you very much.
Matthew, did you want to ask your question? I see that Konstantin has given at least a partial answer in the chat.
Oh, there was one in the chat. Yeah, so yeah, one of the projects going on at ALS is looking at the tomography in dichroic materials. So in order to understand crystal orientation in 3D. And so it's of interest to look at propagation through such a system where you have to worry about the vector nature of the field and perhaps the lateral inhomogeneity. To see whether the approximation that the absorption through a material is just a line integral of some effective absorption coefficient on each voxel, and see how relevant or true that approximation is. I was wondering if XRT could be used as a tool to investigate that.
Well, I never heard of anyone tried anything like this, but again, why not?
Well, it would have to be a full vector propagation with a tensor refractive index.
Yeah, this is definitely doable, but probably it might be really heavy. You would have to define a grid and do some numeric integration if you're interested in some precise values. But this can be done, though it's not easy as I can see it now.
Yeah, wouldn't think it would be easy, but it might be better than trying to develop our own tool to do it.
I see, by the way, that Konstantin had maybe privately commented to me. Konstantin, did you want to answer here?
Yes, if I may.
Please.
So,
sure.
Matthew, you mean dichroic in linear, so
Yeah,
not circular dichroism? Yes, yes. So
circular is not as hard.
Specifically, the crystal properties are all polarization dependent. This is a full theory behind. So yes, all polarization properties, even including the Darwin. The Darwin
this is not
reflectivity domain. So it's not outside of. So you probably know when these quarter wave plates were first introduced, they were considered as far from this Darwin reflectivity domain, far to the left or far to the right, where only one wave exists. No, this is what we do is full polarization properties there. Also
I didn't get there yet. There'll be a slide about it. just
but this isn't diffraction. This is propagation. This is absorption dichroism, and the accompanying birefringence.
So yeah, maybe I'll show a couple more slides later, and this will partly answer your question.
Let's hold that for the moment. One last question in this session. Michael Hagelstein, you have a question?
Yes, I have a question concerning what the last thing that you presented, the monochromators and diffraction in monochromators. When we do XAS, what very often happens is glitches, and the question is whether multiple beam cases can be calculated with your software.
Sorry,
multiple beam cases, so that you have kind of interference between different Bragg reciprocal space phases.
Well, we can calculate complete picture for single crystal diffraction, if you mean that. So we'll see the beams going into all possible directions according to different peaks, and yeah, that is possible. That is also not straightforward and a little more time consuming than regular diffraction, but it is possible if you define your crystal as a single crystal and let it calculate all possible reflections.
Yeah, it would be actually good to have that feature in a double crystal monochromator, and since when you do X-ray absorption spectroscopy, then what you find very often is the intensity variations in your primary beam, say 111, but going through the diffraction condition, you observe from time to time strong changes in the intensity because there are other reciprocal lattice planes giving rise to some interference in the diffraction.
Yeah, right. So this is all it's already there. So you just have to define slightly more complicated model as your monochromatic crystal. And
if I may add, it is still single scattering, so it's not double so more complicated reflections. Only, but single scatterings, yes, they can be many in different directions. So or from different planes.
Yeah, well, I'm really talking about multiple reflections that are kind of initiated by the primary beam, and yeah.
Sounds like this would be a good discussion to continue at the end. The monochromator glitches. Very good.
Umweganregung is the right word for it. Just Wolfgang saying.
Very good. All right, Roman, you should continue, please.
So yeah, now a short demonstration of how I use the material properties model to estimate the flux on the sample. So I've pre-calculated the spectrum, the wiggle spectrum at our beamline, and then I've added all possible all optical elements to simulate the real absorption and reflection. So by default, nothing is in the beam besides our two big mirrors, and already you can easily move this slider, and it shows you the flux that you get. You can even estimate the reading from the ion chamber. So if you click here, MLA, that is current in the ion chamber. It's definitely specific to our beamline, to our dimensions, but that's what our users see. And I basically decided to write this tool when we were getting lots of questions from our users, like where's our beam? Why there's when the intensity is dropping, they used to look at these nice curves with lots of photons, but if you consider absorption in nitrogen that we use in our ion chambers, it's clear that the current and reading from ion chambers will drop. That is normal, and basically these values correspond pretty well to what we really get and what we really see on our screens. And one can see what happens if we add this or that filter, if we change the pitch of the mirror, if we fool the optical line with air instead of helium, or instead of just pumping it. And if we need to work with at lower energies, we have to introduce the harmonic rejection mirrors. And again, when they decide how to align the beamline, they can see, okay, we work at 9 kV, and we probably have to put our mirrors into this position. Or that's really useful, and it helps the users on the beamline understand better what is really happening and what to expect from the beamline. And one more thing that I added there is the crystal reflectivity. It's just plain crystals, no bending. Just to that's mainly just a demo, right? To see how they dive in with changes. And depending on energy and with different asymmetry angles and different reflections. So once again, you can move the slider. This all is now running on my Raspberry Pi, a very powerful supercomputer sitting in the neighbor room, and it's pretty powerful. It takes a matrix, an array of data, and processes it interactively in real time. So if it works on a Raspberry Pi on the fly, it will work on a desktop, on a powerful desktop computer for sure. So again, that's just a demo. Good. I can proceed with the presentation now. So in principle, I'm planning to maybe add a similar calculator to calculate the X-ray sources. Yeah, people, at least now, when we first started designing CLS2, people asking what this or that source look like on a new ring. And I was planning to add a similar calculator to have it online so that everyone could use it and calculate it easily. Good. So I think I stopped here. Yeah, that's where it was. Yeah, good. So we have a lot of examples available. We provide lots of tests and examples with the code, or you can simply view the output online if you visit the XRT documentation page. That is just borrowed from the documentation. Konstantin was running this study, this comparison of different geometries and different configurations when he was building his spectrometer at the Boulder beamline, or maybe even earlier. So it's quite easy to run such simulation when you decide what kind of spectrometer you need, what kind of spectrometer you're planning to use. Yeah. Now the thing about polarization. So we do take care about the polarization and decreasing, and we preserve all the properties via the coherency metrics. I don't know if it answers Matthew's question. Yeah, but we can easily calculate the quarter wave plates and emulate all the changes happening with the polarization of the beam. Good. Now, a few words about advanced topics, the wave propagation. Yeah, I always suspect nowadays that people are interested in running the full wave propagation study. Many people using SAW, and it's becoming more and more popular as the synchrotron switch to lower emittance, and yeah, they start seeing all these effects of the coherency and so on. So we use the most general diffraction formula for the wave propagation, the Kirchhoff integral theorem. Basically, the most important part there is this sum in the middle. Yeah, so we take care about the directions. There'll be one more slide later to illustrate this. So in general, we do treat every ray as a plane wave, and then we see how these waves are interfering. So how the wave incoming from every point of surface of the optical element, how all these waves sum up on the next optical element or in the next point in the space. And this way, we are propagating this wave further and further. And we don't use any grids. So yeah, now this thing. So we don't use any grids. That is relatively slow. It's not the most efficient way to calculate anything. Monte Carlo integration is really resource hungry, but at least we can preserve all the information about the directions and about the complex amplitudes. SAW, for instance, works in the paraxial approximation and only considers the first Fresnel zone, basically. And that's if you go this way, and yeah, if you calculate the Fresnel diffraction, you can use the fast Fourier transform that speed ups calculation seriously, and that is where we lose to other packages. Basically, it's just in the performance. Obviously, fast Fourier transform is much faster than Monte Carlo integration. And just for comparison, with Shadow and the hybrid edition that they've introduced recently, so they say that they only work in a Fraunhofer approximation and basically work with the directions rather than in intensity maps. Directions and divergence. Yeah, so as I said, preservation of the most generic integration form allows us to carefully calculate all amplitudes. And the fact that we don't use any grids and we're randomly sampling the surface allows us to work with gratings and with zone plates, and allows to calculate precisely the efficiencies of these optical elements. It's and this can be used in a real study. You can add a real grating and not only see the change in the direction of the beam, like the diffraction to different orders, but also calculate what would be the intensity of this or that order. And the same, yeah, also the same can be done for the zone plates. We also can do the partial coherence calculations, and we treat our beams the same way as, for instance, SAW is doing it. So we consider each plane, each wave as a purely monochromatic one, and calculate all diffraction effects as for a monochromatic wave, and then we incoherently sum them up so that the waves originating from different points of the source in different direction will sum up incoherently, and this will worsen the interference pattern. And this is a correct approach to emulate partial coherence, so that for the fully incoherent beam we won't see any interference, just not flat, just a smooth peak, and fully coherent beam would have the maximal contrast. So yeah, now to the graphical capabilities. So as I said, it's hard to surprise anyone with a GUI nowadays. Even Shadow and SAW are now included into Oasis, and it is quite a convenient shell to use these packages. But we offer a little more. So we have the live documentation, and we have a tool for 3D visualization of the beamline. And yeah, basically it has all the features as we use for our plotting, but just more interactive. I won't stop on this in detail now. I will rather switch to the live demonstration. So just a few examples. Yeah, you can use this 3D view to see how the beam is changing. Usually, yeah, you don't see the X-ray beam. Yeah? It's invisible, but with a tool like this, you can visualize it. You can see the focal spot, and you can decide what to adjust in your optical element, how to move your screen this or that way, or see, yeah, what part of the beam to choose if you want better monochromaticity. Yeah, like this. And with this, yeah, maybe another few minutes for questions, and yeah, I will then switch to live demo.
I have a question while we look for other questions in the chat. Which beamlines do you know of that have made the most use of this capability? Either beamlines under development or being modified. You know, how widely used is this for the whole beamline in the synchrotron community?
Well, I know many beamlines at Petra are using this. both existing and the ones that are in design. I know, but basically lots of beamlines here and there. We can only judge from the questions that people are asking. Yeah, if they ask something, then probably they're using it or they're planning to use it. And yeah, I'm not mentioning many beamlines at CLS who really try it and see it with my help.
I see.
Well, obviously Max 4, but it's more a question to Konstantin. He knows better who is using it there. All these questions come directly to him.
Okay. All right. I'm gonna. Someone has sent me a message with a question, but we're going to hold off on that until the end. And so you should go ahead with the third piece of your seminar now.
Okay. Fine. So I'll start with the beamline first. A brief overview of how this interactive visualization can be used on the beamline. Okay, let me see. Yeah, I'll take just a standard example. So that's my beamline that I know very well. And everything is already predefined. We have all the optical elements there. Yeah, you can see mirrors, slits, whatever, starting from the Wiggler source. I've generated few materials that we use for coatings and we use in our filters, and already added some plots. Yeah, in order to run real ray tracing. But there's an easier way, there's a fast way to look at the beamline layout, is this 3D goggles button, and that's all done in real time. So I've just calculated, what's that, 500,000, right? So something like that. Yeah, where's the picture? I think I just lost it. That is often happening during the demonstrations. Yeah, maybe I'll just close it. Yeah, and then open it again. Okay. Yeah, let's try one of the models. Okay, that's all standard. Maybe this one would work better. Huh? What? Hey, come on. I don't know if it's related to the screen sharing. Okay, maybe if I remove it temporarily from the screen. Everything was working perfectly right before the start.
Indeed, the curse of demos.
Yeah. Well, I'm not surprised. Okay, let me try again here. So I literally just close this window before I connect to Zoom. Let's try here. Well, that's an interesting glitch anyway. Interference between Zoom and OpenGL. Who would ever think? Yeah, it's done when it's run in a separate window. Okay, I'll just move it here. Hope you see it now. Yeah, for some reason it doesn't want to be generated in the shared window on a shared screen. So that is our beamline. Yeah, I can expand it to the full screen to see better. Yeah, there's some few yeah, buttons for convenience. So automatic adjustment of the scales, and it's independent along different axes. I'll now jump to the sample and maybe, yeah, I can contract it again, because all real beamlines are stretched into many meters. Yeah, so that's how the ideal beam would look like. So that is the screen where the sample is sitting, and that's a nice uniform beam. We don't focus too aggressively because our samples are sensitive and we don't want to burn them. So that's why it's moderate focusing. There's a reasonable energy resolution. So I would be happy if the beamline really looked like this, but yeah, real life is something different. So for instance, we have some additional role in the monochromator. So I'll now add a roll to the crystal, and we'll see what the beam will look like. So let's say it's a little more than in reality. So just to have a better picture. Hey, yeah, something looks different now. So everything is skewed and everything is tilted. Yeah, we don't want this. I will try to correct it by adding some yaw on the first mirror. Why not? So let's add yaw, and it will be 0.3 degree. A. Like this. What is, yeah. It doesn't look much better. So let's add another yaw on another mirror. It will be something like this, probably. Yeah. Now at least it's more or less straight, and the shape is more resembling the real beam shape we see on the beam position monitors. And yeah, you can notice what happened to the energy resolution. That nice narrow peak going out of the monitor is now a little too wide and a little ugly. And in reality, you don't notice that. So if everything is aligned, okay, you mostly see the shape of the beam. You can for sure measure the rocking curve and estimate, but it's just hard to say. It's hard to say where it's coming from. And yeah, this way of introducing misalignment and some inhomogeneities. I could add a real mirror surface here, and then that beam would seem even more realistic with stripes on it, the stripes that are coming from the surface distortions. But that's the most important thing I wanted to show you. We rarely see the beam spectrum on our screens. We can only see profile, but in reality, something unwanted may be hiding there. So it's just to be careful about adjusting different parameters and trying to do things without completely understanding what is happening, what is going on. It's easy to break something just simply by changing the alignment. That's the idea. So yeah, that was example one. Yeah, as I said, in reality, it's not that bad. So it just looks nice and contrast. I hope you see all these colors on your screens just as well as I do. Good. So that was first example with the real beamline and importance of alignment and misalignment. And now, yeah, a small example with the spectrometers. So I may start with just a single crystal and then try to move its position and orientation and see what's happening. So I won't run any calculations to study the intensity, because that is something different. Okay, good. That was here. Let's start with this. Yeah, it did work. Nice. So that is just one of our examples. Maybe it's too many arrays here. So here's the model. In principle, I can try to integrate it. I'm not sure that everything worked as I expected. Yeah, indeed, it's some interference between OpenGL and screen sharing. Okay, I'll kill it now. Yeah. Okay. And just start again a separate window and then move everything back. It seems to work that way. Okay, that is cylinder 3D. Yeah, so come here. Right, okay, let's try it this way now. It's really hard to say what is there. Right, we can feed it all into the screen. So that now looks like some kind of energy dispersive element. What exactly is there? Let's see. So yeah, now it's von Hammer's geometry. Yeah, it's really hard to say what is happening. So I will now just disable all the rays I don't want to see. So I will only show the rays that are falling on the crystal. Yeah, we can do this nice representation here. And yeah, maybe I should even disable these things like this. So what we see now is in an energy-dispersive geometry, in a von Hammer's geometry, it's just a small part of the crystal that's really working. It's just a narrow stripe that's reflecting. That is not a surprise, right? But it's good to see what is happening, yeah, with your own eyes. And then once you decide what kind of spectrometer you use and what size of the crystal to choose for it, yeah, you can look at this and decide, okay, that's probably a little too. Yeah, I'll move it all to 1:1 scale now and set the center here. So yeah, that's a square crystal, but in reality, we could easily work with a much smaller thing, and yeah, maybe even make it yeah, safe on the crystal, safe on the surface, and then we could save some space and add more crystals here. So that's the first example. Then now if we switch to Jochen geometry, I will simply do this by selecting a different incoming beam on the screen. So it would be, please expose the Jochen cylinder beam. This, so now it's cylinder, we disable, okay, bye von Hammer's. Show the surface, and something doesn't seem right again. Yeah, okay, let's disable this beam, and yeah, now it's the full picture. What's going on here? yeah, there's a relatively wide peak. In reality, we work with narrow emission peaks like this. Okay, that's something better. There's not much focusing in that direction, right? Yeah, let's show the footprint. So that is the Johann geometry now. You can see that now larger area of the crystal is working, and that explains the efficiency of the Johann geometry comparing to von Hammer's, for instance. But if we now try to misalign it, and if we change the energy, so no, it's not von Hammer's, it's Johann. So right now I use automatic alignment, and yeah, if I now try to go a little away from the optimal values, okay, what if I go now? What would happen? Yeah, see, the profile, the footprint changes, and it's where you have to take care about the real dimensions and real properties. And what if we go up by 1 eV? So that just means I slightly misalign the pitch of this crystal. So now it's getting more narrow, and that means that the intensity that is coming on the detector is dropping. So you have to be very careful about the alignments. Okay, let's now go back here, and okay, let's change the curvature. It's 1 meter now. Let's say it's 9 millimeters. Yeah. Again, something completely unwanted changed, and you can only indirectly see this based on the picture on your detector if you don't use any focusing, because now you can notice that the shape of the spot on the detector changed, and this would mean that something is probably wrong, that the bending is not perfect. And if I define some underbending here, yeah, the pictures are similar, but it looks absolutely different on the crystal. And with this tool, it's just easier to understand what is happening and what to do. So you first look at your detector. Okay, you have no idea what's happening. Then you open the model and try to play with this model in real time and see what it ends up, what you have in the end. Okay, let's go back to optimum, and it really looks much better. Yeah, now we can try Johansson. Let's see what Johansson look like. Maybe before we go there, yeah, I can try the flat distribution. Sometimes it's more. No, that is wrong. Yeah, I don't see the dogs here. Can I? No. Hey, come on. Yeah, didn't like it. But anyway, if you're running it on a local computer without screen sharing, you would see the live documentation and all descriptions, all comments regarding the parameters used in the definition of different optical elements. It's just a little tricky to do it, yeah, when it's on the shared screen. How to see why? Okay, I'll just do it again. That is here. And this thing. Okay, let's get back. So I was meaning, yeah, I could just click live doc and all documentation will be available just right away. So in principle, if you want to study the intensity, so you already have your predefined model, the easiest thing would be simply just add a plot. So there will be a beam, an output beam, and you can right click it and add a plot and then generate a script. Yeah, set the number of repeats here. So usually when you work with energy discriminating elements, even if you generate maybe a million of rays, what comes to your sample, what comes to your detector is maybe a few thousands. And if you want to have better statistics, you would repeat this multiple times. So you would just change this number of repeats and run the simulation, and you would have a nice plot with some reliable numbers in the end. Okay, good. Let's get back to the elements. So it's still for cameras. Okay, I don't mind. Okay. Feed it all. So yeah, Johansson. Maybe will be just one of these and then one short script, just a demonstration of multi-element analyzers. So yeah, again, I only need to choose a different input here. So physically, obviously, it's not possible to place several crystals into a single position altogether. That's only done for convenience. I have them all. So okay, now let's do propagation with Johansson type analyzer. Okay, I'm disabling the footprints, adding the surface here. Okay, did I? Yeah, okay, we don't want this and we don't want this. And probably we don't want this as well. It looks like my Johansson crystal is smaller, right? Let's make it the same size as previous two. Good. So yeah, again, you see, even larger area is it's exposed, is participating in the diffraction, and what is coming to your detector is coming from a larger area. And if we have this narrow source, let's see, half a V, it would be, yeah, a little more narrow, but it's much more intense. It's way more efficient. And if you again now try to break everything and change the, yeah, if you change the pitch, see the intensity is dropping. If you just slightly change, yeah, move it slightly to the other side, yeah, again, similar thing is happening. If we had a bigger crystal, like vertically much bigger, we would see, yeah, some fancier shapes. Okay, now ending. Okay, yeah, something similar to what we had on the Johann type. Okay, here. Yep. Yeah, so that's one thing. So you can use it to look on your detector, then try to reproduce it in a model, and then decide, okay, I need to do this or that to make my setup optimal. And that's all in real time. That's very it is intuitive. Yeah, it's easy to play with it. At least you see what is happening and where it's happening and how it affects your picture. So I will now close this and just one last example with multiple elements. So in principle, I have some helping scripts that generate all these kinds of multi-crystal analyzers for me in different shapes. If I just move it here in the code, I simply define the configuration, how many elements along in horizontal and in vertical. I defined the orientation, positioning, and material type. So here it's basically just silicon and different reflections, but you can adjust the size, spacing, and so on, radius, and the script will generate whatever you desire. Hey, what was this? Jochen. I just run it 3x3. I don't know if anyone is using this 2D. It could be just an exercise. Because right, I forgot that it doesn't like this screen. Okay, wait a second. Okay, so here it goes. All your crystals. It's easy to notice that it's hard to focus onto the same spot because these crystals have to be in different positions and at different angles, and there's no way you could really focus into a single spot with the detectors distributed laterally. Vertically, it's not a problem. I mean, vertically in this configuration, but with detectors lined up horizontally, they will always try to focus into different spot. You could try moving the screen back and forth and see maybe find some compromise. If your detector is big enough, maybe you don't really care about this difference in the wavelengths, but it helps you touch it and feel it and decide, okay, maybe I don't want this kind of setup. Maybe I just want something different. Like I only want to line them up in one direction. Like this. This one. Yeah, it's coming. So with all the crystals line up in the transverse direction, it works much better. Maybe there's some space for improvement here because I'm pretty sure it can be focused, or maybe I already added some misalignment. That is also possible. Yeah, so this one is misaligned. What if I change it to optimal? Yeah, so yeah, but it looks better. Now we have just two spots, and okay, what's with the third crystal? Yeah, it's also misaligned. Yeah, it looks much better now. So all your crystals are aligned perfectly and working at 100% efficiency. And yeah, you can work with it. Your alignment is done. And it's again useful during the design and during the troubleshooting. Yeah, helps you understand what you're getting from your real equipment. And that's all probably that I wanted to show today. Yeah, now we are a little late already. I don't know if
we'll do just a question or two. Yeah. Michael, you had a follow-up question.
Yeah. My question is whether you're prepared to help people when they have their particular problems, ray tracing their beamline or getting stuck in it somehow. I remember trying your program, your software some time ago, but I didn't succeed in the end. So I don't remember why I had the problems, but how do you interact with your, say, customers?
Well, I already mentioned that we encourage everyone to submit their issues to GitHub so that it would be visible to all people. So probably if you have a problem, I doubt it's specifically your problem. I would imagine that many people have it, so that later when someone else comes across the same issue, they would just hopefully read through the GitHub issues and find that solution before they ask us questions. So yeah, GitHub is the preferred way we want to get the feedback.
Okay.
It's not always immediate. Sometimes it really takes time to understand what is happening there, but we try to answer everyone.